In the malonic ester synthesis, we're combining a few things that we've learned. So basically the process that's going to take place here is a three-step deal where we'll first do an alkylation, second we'll do a hydrolysis, and third we'll do a decarboxylation. Although remember, the second and third steps you can actually combine together. So we're going to start with malonic ester. So the wording can be a little confusing here because we're not actually synthesizing malonic ester. Malonic ester is our starting material. So let me show you what that looks like. Here is malonic ester. And what you should already know about this is the fact that we have these alpha protons, and those are more acidic than just regular alpha protons because they're flanked by the two carbonyls. So we can alkylate at that alpha position. So that is our first step. So we'll first start with a base. And an important feature if you're alkylating an ester is that you want the base you're using to match your ester. If not, then it can convert one ester into another ester and give you a mixture of products. So always try to match your base with your ester if the ester is a starting material. And then we'll do the second step. Let's say you want to put an ethyl group at the alpha position. We can use something like ethyl bromide. So the first thing that happens in the presence of the base, we form the enolate. That will take one of those alpha protons. Giving us this nucleophilic enolate. And then when you add the ethyl bromide, that'll alkylate this to put the ethyl group on the molecule. Like that. All right, now from here, if you wanted, you could do a second alkylation. And we'll come back to that and look at the potential for a second alkylation. But let's go ahead and just take this forward. So this is our first part where we do the alkylation. The second part is the hydrolysis. So we do acid and water. That'll hydrolyze the esters to carboxylic acids. We still have the ethyl group on there. And then you can heat this, and that'll do a decarboxylation. And we have two carboxylic acids, so it doesn't matter which one you pick to lose. Let's just say we lose this one. And you can only lose one, not both. And here's our product. So to recap, here's 1, the alkylation, 2, the hydrolysis, 3, the decarboxylation. Now, as I mentioned before, you can actually do a second alkylation. So say you wanted a product with 2 groups on here. If you wanted an ethyl and a methyl, you can do a second alkylation at this stage. We put another alkyl group at this position and then decarboxylate that to get the product. Here's an example problem for you to try, where we're starting with the malonic ester, but you'll notice in this case, we've done 2 sets of alkylation conditions. So we have a base followed by iodomethane, then we add base again, followed by this benzylic bromide, and then finally we do the hydrolysis and decarboxylation. So I would recommend you pause the video, see if you can predict the product, and then you can resume it to see the answer. So in this reaction, we treat it with base once, followed by iodomethane. So after steps 1 and 2, what we end up with is a methyl group added at the alpha carbon. Then after steps 3 and 4, we add a new group. We still have the methyl, but now we need to add CH2 and a phenyl. Like that. And then finally, step 5. Step 5, we do the hydrolysis, which gets rid of the ethyl groups and converts those to carboxylic acids, and then you lose one of those CO2. So in the end, we end up with the carboxylic acid. So we'll have the methyl attached, the CH2 phenyl attached, and that's your major product. If you want to write out the byproducts of this, in the hydrolysis, we lost 2 ethanols. And in the decarboxylation, we lost CO2. Let's work through an intramolecular variation of this. And basically what that means is we're going to add our base and our organohalide, but this organohalide is a dihalide. So instead of adding 2 different alkyl groups, we're going to alkylate at this position and then alkylate from this position in an intramolecular version, meaning that second step is happening within the molecule. And basically, you're just adding enough base here to allow this to stir in the presence of the base to do the alkylation at both sites. So the first thing, let's just go ahead and do this stepwise. We get our enolate and add the dibromide. And that'll attack one of those carbons. You'll lose bromine as a leaving group. So here's our new bond, and we have 2 carbons and the other bromine. Right, from here, If we leave this in the presence of the base, we'll form the second enolate. Like that. But now, instead of adding a second organohalide, your other organohalide with the leaving group is already right here in the molecule, set up, ready to react. So this can attack that. That's a nucleophile and electrophile. Lose bromine as a leaving group, or bromide as a leaving group. And in this case, we form a three-membered ring, so you get the cyclopropane structure. Now, when we do the hydrolysis and decarboxylation, we'll convert the esters to carboxylic acids. So those become OHs, and then you'll lose one of those as CO2 gas. So in the end, you get the carboxylic acid bonded to the ring. So this is actually a really good method to get a carboxylic acid on a ring.